All right, so we are starting three-dimensional figures. They are not new to you. We talked about 3 dimensions a little bit at the beginning of the year when we did points, lines, and planes. These figures are not new to you. You literally start learning the names in kindergarten, okay? Now, the more specific things that we're going to do with them, you've not necessarily seen, but you have done surface area and volume, and you know the names of them, things like that. This is going on page 94 when we are done. All right, so we have a generic name for a two-dimensional figure. Like if I have a hexagon, octagon, nonagon, what's one word that can generalize all that? Polygon. Okay, so a polygon is a generic name for two-dimensional figures that have at least 3 sides and closed plane figure, all that kind of stuff. So to get a generic name for some three-dimensional figures, not all three-dimensional figures, but some of them, it's not a polygon, but it is a polyhedron. Okay, so a polyhedron is a three-dimensional figure whose surfaces are 4 or more polygons. So they're polygons that are put together to make a three-dimensional shape, which again, it doesn't classify all three-dimensional figures, but it does classify some of them. Okay. All right, so if we look at this figure right here, what's the most generic name you can give this thing? What is it? A prism. Okay. So this is a prism. So a prism is formed by 2 parallel, this is important, 2 parallel congruent polygonal faces. Okay, so the bases, and they're called the bases can be any polygon. In this case, they are triangles, but it doesn't have to be a triangle. It could be a hexagon, an octagon, whatever. So a prism is formed by 2 parallel congruent polygonal faces called bases, connected by faces that are parallelograms. So I would be willing to bet that most of you didn't think parallelograms was going to go in that blank. What did you think went in that blank? He said thought squares. Most of you, if I told you to fill that in, you wouldn't have put parallelograms. What would you have put? What have you seen mostly? Rectangles, okay? Which sometimes could be the squares as well. Because most likely, most, if not all, of the prisms that you have dealt with up until this point have looked something like this, bless you, where the lateral faces are rectangles. Am I right about that? Okay. And they can be. They absolutely can be. And that may be the only thing that you've ever actually seen. But this right here, this is a prism as well, right? It still has 2 congruent parallel bases, but these lateral faces are not rectangles. They are parallelograms, okay? Are these faces parallelograms also? Yes, more specifically, they're rectangles, but this right here just takes care of all of it, okay? This is a right prism, and we'll talk about the differences between these a little bit tomorrow, but that's why it has parallelograms there, not rectangles, which is probably what you were expecting. And then these are pointing to the bases. The other thing you have to make sure that you pay attention to with prisms is what the bases actually are. And the prisms are named by their bases, so are pyramids, but they are named by their bases. Most, if not all, prisms that you have dealt with when you found surface area and volume and everything else up to this point have probably been sitting on their bases. Maybe all of them, but at the very least most of them have been sitting on their bases, which leads you to misconceptions. It leads you to think, without realizing you're even thinking that what it's sitting on is the base, and that's not the case at all, right? Because this is a triangular prism. Would we all agree with that? Whether I hold it like this or I hold it like this, is it still a triangular prism? Yes, but one of the most common mistakes that happens to a lot of people, no matter how many times I go over this, is that if it's turned like this and it's sitting like this, then somebody uses the base as to be the rectangle, and that's not the case. Okay, if this is a triangular prism, the 2 congruent parallel bases are the triangles. Whether it's sitting on a rectangle or not, it doesn't matter. But in our minds, I think we think about the base being the bottom of something, which a lot of times it is. But think about the base of a lamp. You have a lamp, right? You know which part's the base. If you lay the lamp down, does it change what part the base is? No, it doesn't. Okay, so same thing with the prism. When you lay it down, it doesn't change what the base is. It's not necessarily what it's sitting on. Okay. All right. So then what is this thing called here? Cylinder. All right, so a cylinder is formed by 2 parallel congruent circular bases and a curved surface that connects the bases. So for a prism, the base can be any polygon. But for a cylinder, it has to be a circle. That's your only option. Is a cylinder a polyhedron? Yes, no, maybe? It doesn't have any polygons, does it? No. Okay, so it's not. Just like a circle is not a polygon, right? A cylinder is not a polyhedron. Some of y'all were focused on the 4 or more. There was only 3 pieces, and you're right about that. But none of them are polygons anyway, right? So there are no polygons. So a cylinder is not a polyhedron. That's okay. Everything doesn't have to be. I mean, not everything's a polygon either. So we're good. Just make sure you understand what the definitions actually mean. Okay, so in general, what is this thing here? Pyramid. Okay, so a pyramid is formed by a polygonal base, right? That means the base could be any polygon. In this case, it's a triangle, but it could be a hexagon, an octagon, whatever. But some sort of polygon for the base. And what do you think has to be true about the other faces that are not bases? What do they have to be? Triangular, good. And triangular, you are on fire today. And triangular faces that meet at a common vertex. Now, what kind of triangles they are will depend on what kind of pyramid it is, but they're triangles no matter what. And they meet at a common vertex. In this pyramid here, how many vertices are there? 4, right? There's 4 vertices. But do you remember with an isosceles triangle, how an isosceles triangle has 3 vertices, but one of them is the vertex of the triangle itself? The same thing happens here. There are 4 vertices, but the one where the lateral faces come together, this is the vertex of the pyramid itself. Okay? And then this would be the base. Then what's this next thing? Cone. So a cone is formed by a circular base and a curved surface that connects the base to a vertex. Now, the vertices usually are where the edges meet, okay? And the edges are usually where faces meet and will be line segments of some sort. But we have a vertex here where we don't even have any edges and we don't have any line segments. There's only one vertex. Oops. It's still the vertex of the cone, but it's not like you have to stress it as much because it's the only one that exists anyway. But it is the vertex of the cone, and this is the base. Everybody good? Okay. So basic figures that you've known before, but make sure you pay attention to some specific things about them. We name prisms and pyramids by the shape of their bases, right? And I know you know the difference between a prism and a pyramid, but sometimes the wrong word comes out of our mouth, and sometimes that causes you to use the wrong formulas and do some other things wrong, so make sure you're thinking about it. Yes, it's simple. Yes, I know you know the difference, but it's really easy to mess that stuff up sometimes too. So what would we call this thing here? Triangular prism. Good. So this would be a triangular prism. So what would this thing here be? Good. Triangular pyramid. Yeah, it helps to pay attention to what I'm pointing to. Then what would this be? Good. A rectangular prism. And what would this be? Good, a rectangular pyramid. Okay, is it possible that that could be a square pyramid? Yes. Is it possible that could be a square prism? Yes. Okay, do we have enough to know for sure whether or not that's a square? No. Do we have enough information to know for sure whether or not it's a rectangle? Yes, because a quadrilateral with 4 right angles is a rectangle, right? So this is for sure a rectangular pyramid, for sure a rectangular prism. If this was a square prism, would that mean it has to be a cube? No, because it could be tall and skinny, right? I could have this 2 squares as the bases, like a skyscraper or something. The bases could be squares, but then the sides just be long rectangles. But this even could possibly be a cube if all the sides were squares, but we don't know. We don't have enough for any of that, but this is the best we can do, okay? So what would you call this thing here? Well, it's a pentagon, so it would be a pentagonal, or pentagonal, it's tomato, tomato, right? Pentagonal prism, which means this would be a pentagonal pyramid. And then that would make this a hexagonal prism and a hexagonal pyramid. All right, everybody good with all that? Any questions at all? All right, so if you're, sometimes when I walk around and people are using the wrong thing for the base and doing the wrong work, I'll say, okay, what is that shape you're working with? And be like, oh, that's a triangular prism. Awesome. If that's a triangular prism, why are you using the rectangle as the base? And then they look at me like, oh, good point. So make sure you're thinking about what you're doing, because there's times y'all don't even agree with yourselves. Like, I know you can tell me what it is. Well, then you're telling yourself what the base is. So we're not even doing any surface area volume today, but I'm going to repeat myself every single day about that to hopefully minimize those mistakes. But we'll see what happens. All right, next page. So this is a two-dimensional figure that we could cut out and fold up to make into a three-dimensional figure. So what is that two-dimensional version called? I'm not asking what it makes. I'm saying any two-dimensional figure that you can fold up to make a three-dimensional. Starts, it's a three-letter word. Starts with an N. A net, yes. So a net is a two-dimensional figure that you can fold to make a three-dimensional figure. So if we took that net and folded it up, what three-dimensional figure would we get? Rectangular prism. Now, this visualization, the three-dimensional visualization is more difficult for some people than others. It has nothing to do with how smart you are. It's just how your brain is wired to visualize those things. As soon as we flipped to this page, there were some people that are probably looking at that like it's already folded up in their mind. It's like rotating and they can describe it to you from different angles. And other people are still struggling with how the heck you even fold that up in your brain. So, and if you're struggling with it, it should get a little bit better. But if you don't struggle with it at all, sometimes it's difficult for you to understand that people actually have problems with it. So I'm going to give you some pointers on how to help you if you do have trouble visualizing that stuff. I know not all of you need it, and so I'm not saying you have to do it, but it's more for the people that really are having trouble, like knowing whether or not these would fold up to make a cube. Again, some people could already look at it, already have the answers. Don't say them because I don't want to hear them. But other people are like, I hate this stuff. I never can figure this stuff out, right? So I'm going to give you a way to do it with like labeling, so you can kind of do it a piece at a time, because you're not going to be able to cut things out and fold them up on tests, right? So you've got 6 pieces if this is going to make a cube: a front, a back, a bottom, a top, a left, and a right, right? I don't know. Top, bottom, left, right, front, back is what I meant to say, whatever I said. So we're going to label them and see what happens, and you can kind of fold it a piece at a time instead of trying to visualize where the heck everything's going. So we're going to pick like a central piece. This looks good. We're going to make this the front. So if this is the front, then this would flip down and this becomes the top. Does that make sense? So this would fold around, this would be the right, this would keep going, and this would be the back. And I have to put BA because we have a back and a bottom. Then this is the front. This flips underneath to become the bottom. This is hanging out over here so it can flip up and become the left-hand side. And so I have a front, a back, a top, a bottom, a left, and a right, and this would make a cube. So do you see how if you label it, you can kind of do it a little piece at a time instead of trying to take it all at once, which is too much for some people. Okay. So let's do this one. Make this the front. So that would make this the top. This would fold behind and become the back. This would be the right-hand side. This would be the left. And then it keeps going around, and this would be the back. So is that going to make a cube? No, because the bottom is open and there's an overlap in the back, so this one does not work. Okay. So then we can pick this as the front. It doesn't matter which one you pick. It just makes it easier if it's kind of central. So this can flip down and be the top, which means this would flip over and become the right-hand side. This goes underneath and become the bottom. This would keep going around and become the back. Then that's sticking out over there, and it can flip up and become the left. Okay, so does that work? Yes. So we can make this one the front. This would be the left and the top. So the right and the back. As that flips around, this is still hanging down, so this can flip up and become the bottom. So this one works as well. So I'm not saying you have to label to do those, but I know there are some people that need something like that to make it work, because otherwise it just doesn't work in their brain, and that's okay. But you got to work on that visualization a little bit, because we're going to get into some wacky stuff here towards the end of all this. All right, so let's look at something that's most likely a new term for you in a concept for three-dimensional stuff. And so if you look at this, say that this was a cube to begin with, right? And then somebody came and sliced a corner off. It's like a plane came through and just sliced that right off. The chunk that fell off would look like what? It's a pyramid. It'd be a triangular pyramid, right? If I just slice the corner off. Okay, but what we're looking for with these is not the three-dimensional part that gets cut off, but it's the two-dimensional part that's left. And this is what's called a cross-section. Okay, so a cross-section is the face, which means it is a two-dimensional answer. Face you get when a plane slices through a space or 3D figure. Below is a sample slice through a cube showing one of the cross sections you can get. So a cross section is like, if I want to try and sell you a Snickers and tell you why Snickers is so great and why it's so much different than Milky Way, well, if I just unwrap them both, they pretty much look the same, right? Until you cut it in half and then I turn it and show you the inside like on the commercial, right? That's a cross section so you can see what's going on inside. If I slice it the other way, I might only see the caramel, but if I slice it, through a certain way, then you can see all the layers of the yummy stuff. So what we're looking for here is what is on the inside. It has nothing to do with what's on the outside, and it's always a two-dimensional answer. Okay, so this right here is my cross-section. Yes, a triangular pyramid gets chopped off, but the cross-section is a triangle. Okay. So the plane or 2D figure formed by the slice is the cross-section. The cross-section cannot contain any piece of the original face. It all comes from the inside. Right? And you can think about these things being molded out of like Play-Doh. And you have them in front of you on a cutting board, and you have a big butcher knife that can represent the plane. And you're just going to slice right through it, and then what would you get? It can kind of help you visualize it instead of trying to cut three-dimensional figures. And that's what we're going to do with these down here. Now, I deliberately left off the directions because I didn't want anybody to get ahead of me. So I'm going to give you what we're going to do here. And I don't want you screaming out what you think it is because I want everybody to have a chance to think through it. So picture this being Play-Doh in this shape, okay, that's in front of you, right? And you have a big butcher knife that you're going to be able to slice through because that's like your plane coming through. And we're going to do this parallel to the base. Okay, so if it comes through and slices parallel to the base, think about what you would get with the cross section. Okay, I'll give you a second to think about that. You're going to slice through. Your knife is going to go through parallel to the base. So I want to know, what would the cross section look like? All right, who wants to tell me what they think it is? Amy? Okay, Amy says triangle. What does Parker say? Parker thinks it's a triangle as well. Does anybody disagree with these two? Okay, so good job. So if you think about this, okay, because sometimes you're going to have a hard time visualizing what it's supposed to be. So think about if you set your knife down right here, and it's going to have to go through and be parallel to the base, then it's going to come through and slice through this way, right, and then come out the back and look like that, and that is what you get, which is a triangle. Okay, does that make sense? Now, it gets chopped into two smaller triangular prisms, but that's irrelevant. Nobody asked you for that. I mean, it's good to be able to visualize that too, but that's not what the cross section is. All right, so on this one, we're going to do this perpendicular to the base. Okay, so again, think about it. Don't yell anything out. All right, who wants to tell me what they think it is? Go ahead. Rectangle with a big question mark on it? Anybody have anything different? I love it. Y'all answer like rectangle. Anybody have anything different besides rectangle? Do y'all agree with her? Okay, so let's think again. Let's try and draw it before we know what the answer really is. We're going to go perpendicular to the base, which means it's going to have to come through the top, right? So if I set my knife down right here, and it's going to come down and be perpendicular to the base, then it's going to have to come out down there, right? And when I follow the path of the knife, that is going to give me a rectangle. Very good. Thank you. Oh, that does not look like a rectangle. It'll respond in just a second. There we go. Let's see if I can draw something that looks a little bit more like a rectangle. That's not great, but it's better. Everybody good? Okay, so the next set of instructions is a little more elaborate because I was trying to lead you down a specific road. So I'm going to give you a second to get it all written down, and then I'll go check roll while you try and wrap your mind around what I'm trying to say here. So we want to make this slice that is not parallel or perpendicular to the bases, passes through both bases, and through consecutive sides. Okay, so I know that's a lot to wrap your mind around, so I'm going to give you a second. I want you to think about what that means, see if you can kind of visualize something. Then I'm going to come back and I'll get you started on it, and then I'll let you think on it just a little bit more. Oh, just to use, oh, that's a good question. It's really not a cube even, it's a rectangular prism. But for rectangular prisms, we are just going to use what they're actually sitting on as the base. Because really any of them could be the base if it's a rectangular prism. We don't know that for sure. So the general rule is then just go ahead and use what it's sitting on. But that's a very good question. Okay, so I'm not going to give you the answer, and I don't want anybody to give me the answer. I'm just going to get you started on it, because sometimes, because of my weird wording, people don't even know where to start and what I mean by all this. I know it's got to go through the both bases, which we're going to use the top and the bottom for this. And then it has to pass through consecutive sides. So it has to pass through two sides that are next to each other. It could be these two or these two, but I'm going to use these two. So when I set my knife down on top of this, I'm going to set it down like right there. So if you're going to start right there, that way it's going through consecutive sides. It would go through that top base. I cannot go perpendicular, right, because it says not perpendicular. So I'm going to have to go through at an angle. So then think about what you think that might look like. See if maybe you could get it drawn. And then I'm going to help you draw it before we even talk about what it is. Because we're going to get into some kind of crazy stuff towards the end of three-dimensional figures, where you're not going to be able to visualize it all before you draw it. So you have to learn to be okay with trying to sketch in what the process, and then when you're done, your answer will be right in front of you. And it's okay that you didn't even know what you were going for to begin with, okay? So if I'm going to start here, if it was going to go perpendicular to the base, then it would come out kind of right here and be spaced the same, right? But that's not what's like, I can't do that. So I've got to back it up some because I'm going through at an angle, so it would look more like this coming out through the bottom. Right? Or something close to that. Yours wouldn't have to be exactly like mine. But if I start here and I go through at an angle, I would end up farther back, right? And so when I did that, if I followed the path, which means basically I just have to connect the dots here, then what is my cross section going to be? What is that thing? A trapezoid. So do you see how just by thinking about how a cross-section is made, once you draw it in there, your answer is looking at you right there, okay? And so this gives you a trapezoid. So if you're freaking out because you have a really hard time with this stuff, don't freak out too much because we don't do a whole, I mean, you have to understand the basic concept of this, but I'm not going to give you like super crazy ones that, you know, would hurt anybody's brain. But you can't be too afraid of them. And I know for sure it's a trapezoid because I knew it was a prism, which means those have to be parallel because the bases were parallel. Okay. Everybody good with that? You good? Yes? Awesome. All right. So now we're going to look at, if this will turn, this. Now, on this page here, I'm really just kind of introducing you to some stuff. I want to introduce you to some terminology, because these you really get into way more in depth in Algebra 2. But there's 5 of these things that we're going to talk about. 3 of them you already know. But for whatever reason, we don't make the geometric connection even in geometry. It's not even part of what I'm supposed to do. But I'm going to because I think it's important. We're going to look at these things that are intersections of a plane and a cone. So they're cross sections, a plane coming through and slicing through a cone or a double cone. And I'll talk to you about what a double cone is in just a minute. So since they are cross sections of a cone, these are called conic sections. Conic referring to cone. So these are conic sections. So this is a cone, right? Here's my fancy cone. This is what makes it a double cone. One's inverted on top of the other. And then planes pass through and things get sliced off and things happen, okay? And sometimes you need both cones, sometimes you only need one of them. That's why it says a cone or a double cone, but this is what's meant by a double cone. And so we're going to graph each one of these, and then we're going to match them to these conic sections that we have down here that shows the cones with the plane slicing through, all right? So let's start with this first one. And it says we're going to graph this y equals x. So when I graph this thing, what is this thing that I would graph? What is this going to graph me? This is not a hard question. It's a what? It's a what? It is not a vertical line. It is not a horizontal line. But it is a, just one word. Line, thank you. It graphs a line. Okay, that's all I'm going for right here. What does it graph? It graphs me a line. Now, it does graph me a specific line, right? What's the fancy words for the specific line? It's some sort of function. Everybody has 2 of them biologically. Parent function. Okay. All right, so it is a parent function. Is this an easy line to graph? Yes. Is it a horizontal line? No. Is it a vertical line? No. What's the y-intercept? 0. What's the slope? 1. Should I really have to overthink it when I graph this thing? No. Okay, so when you graph it, it looks like this. Okay, and this is a line. No brainer, we can graph a line, good deal. Now, that's one of your conic sections. So when you look down here, which cross section does it look like that would match up with? The cross section is what you get when the plane slices through. When this slices through, I do not think that's a line. Okay, E, right? So it's like the plane goes through and just kind of shaves off a line, right? So E, this would be my, so I'm going to cross it out because we're going to use it. And that matches up with this one. So this is E. Okay, everybody okay with that? Now look at this thing right here. This equation would graph me what? We learned them this year. You did not do anything with a y squared in Algebra 1. You did it not too long ago. This just further proves that nobody really listens to anything I say. Nothing sticks. It's not a parabola. We have not graphed parabolas in here. I taught it to you. You had never seen it before. It does make a circle. It does graph a circle. That explains the test grades. So for this circle here, what is the radius? 3. What's the center? 0, 0. Okay. So here's my center. I'm going to go to the right 3, left 3, up 3, down 3, and then I'm going to graph this the best I can to make it look like it's a circle. Okay, and there's your circle. This is the circle. And then we are going to graph this on the calculator as well, but don't touch your calculator yet, because I can't put it in the calculator like that. What form does anything have to be in when you put it in in these calculators to graph? Okay, so y equals mx plus b, slope, intercept, those are forms of a line. Is this a line? No. Do you have to put every line in y equals mx plus b form? No. But you do have to have everything in y equals, right? Because that has to be, that's where you go in the calculator, right? Y equals. If you don't have it set equal to y, you don't have anything to type in, right? So we're going to go over here and we're going to solve this for y. So I'm going to subtract x squared from both sides. So y squared equals 9 minus x squared. Then to get y, I'm going to take the square root of 9 minus x squared. So now go to your calculator and make sure you have cleared the RAM. That is so important because we changed some settings and I want them changed back before you type things in. Now when I take the square root, does that give me 3 minus x? No, it doesn't. Even if it did, who cares? Because the calculator will do it for me if it did. So I'm going to go to y equals. If there's anything in there, that means you did not clear the RAM. And I'm going to type in square root of 9 minus x squared. Okay? And then graph it. Was that a little disappointing? Yeah, because we know what it's supposed to be, right? What is it supposed to be? A circle. That is totally not a circle, right? So why do you think we have something missing? What's missing? The bottom half. What does every point that's in the bottom half have in common? A negative y value, right? What's wrong with my y equals over there? What's it missing? Plus or minus. Every single time you ever solve anything and you take the square root, you have to make it plus or minus. That's huge. All right? So you come, because these calculators only graph functions. Is a circle a function? No, but the top half is and the bottom half is, so you have to graph them separately. So we go back into y equals, go to y2, and then type in negative square root of 9 minus x squared. Okay? And then graph that. So it's better. Are you still a little disappointed? Yeah, because what's wrong with it? It's an oval. Is it supposed to be an oval? No, we know it's supposed to be a circle. I mean, even the circle I drew looks better than that, right? So why do you, we typed everything in right. Why do you think it looks squished? The scale? Kind of, yeah. Why do you think, because really, I mean, if we're not going to go mess with the window, because you don't go mess with the window unless you know exactly what to type in, and you don't know that, so we're not going to mess with it. But the default is to go from negative 10 to 10 and negative 10 to 10, which it does. So why does that make it look squished? What's the shape of the window? The screen? It's a rectangle, right? Aren't your little grids on graph paper squares? Yeah, so it kind of has to do with the scale. It's because we are going, the y and the x are the same, but the y has to be squished to make it fit, right? So why need it to be unsquished? Well, I can play around with the window, but I don't have time to get that all right. And you don't have time for that. Y'all need to stop trying to do so much on the calculator and learn how to make the calculator do it for you, because you don't know how to make it. So those of you that are pushing buttons and trying to fix it, you're never going to get there, okay? So instead, we want the calculator to do it for us. So you hit the zoom key, and you see 5 where it says z square. It's going to square up your graph for you so that it isn't squished. And so 5, and then bam. So here's something that you probably never realized if you didn't even know that button was there. Every single graph you have ever graphed on these calculators has been squished. So your lines, the slope has been off a little bit. And the parabolas are a little bit squished because it is a rectangular window and you probably haven't changed that sort of scale with it. But when you square it up, it actually makes it look more accurate. Now, the lines and stuff weren't off enough to matter, but it matters on other things. It makes them look wrong, okay? So we're a whole lot more excited about this, but still a little bit of disappointment with what? These little spaces here, right? That's just because the resolution on these are so terrible that it was just missing a little pixel there, but it's a circle, okay? Are we good? Now let's look down here at this, and which conic section do you think the circle would be? B. So I'm pretty confident it's not A. Would you agree with that? B looks pretty good. We already did E. What about D? Kind of looks okay, right? And then C. Like, do you have enough knowledge about any of this to know for sure that it's one of these besides the other? Like, do you know? I mean, what? I'm sorry. That was a bad way. That was a really bad way to phrase the question. Could you narrow it down to B and D? Yes. Do you have enough to say it's definitely one over the other? No, probably not at this point. But I think we can narrow it down. So we're going to just stick with, we think it's B or D for right now, and we've at least narrowed it down. And we'll come back. Maybe we could make a better decision after we looked at something else. Okay. So this next one here, what is this going to graph? A parabola, right? You did that in Algebra 1. So to graph that, I'm here at 0, 0. When x is 1, what's y? 1. When x is 2, what's y? 4. Okay, so then when x is negative 1, I'm at 1. When it's at negative 2, I'm at 4. Okay, and then we can go in here and sketch that in. And we know that this is a parabola. So a parabola, just like a line and a circle, those are all conic sections. Again, nobody ever said those words to you, but they are conic sections. Now, let's look down at what we've got here. I'm pretty confident well, we know for sure it's not E. Pretty confident it's not B or D either. But what about A and C? A or C? Because here's what C looks like from the cone, right? Here's what part of A looks like. Have you ever seen two parabolas together like that? You only had one, but did you do like everything there is to do with parabolas? No. So right now, maybe there could be two. Like, we don't know, right? But could we narrow it down to A or C? I think we can be confident in that. So we'll put A or C, and then we'll move on. Okay. Now, this next one, I don't expect you to know what this graphs. You haven't learned these yet, but we're just going to let the calculator help us out to graph it. So in order to do that, I have to set it equal to y. So this is going to give me y squared over 9 equals 1 minus x squared over 4. Then what do I need to do to get y squared by itself? Multiply by 9. But look, you're about to put something in the calculator. Don't go distributing and simplifying things. You're going to let the calculator do all that. So this gives me y squared equals 9 times 1 minus x squared over 4. Don't even waste your time or possibly messing things up by doing anything else. But then I have to take the square root, so y is equal to square root of 9 times plus or minus, good, x squared over 4. Okay, plus or minus, we can't forget that. So let's go and graph this, and that's an x squared over 4. My handwriting's bad. So we're going to go to y equals. I'm going to clear these out, and then I'm going to type in square root of 9, got to make sure I use my parentheses, 1 minus x squared divided by 4, and then negative, make sure you're not using the minus, if you're using the negative, or you'll be getting errors, 9 parentheses, and then graph it. What does that look like? This looks like an oval. Now, last time we had an oval, it was supposed to be a circle, and it was squished, but we knew it was supposed to be a circle, right? Here, you don't know what it's supposed to be. I do, but you don't, but that's okay. But it's not squished because when we squared up our graph, when we did the zoom squared, we didn't undo that. So this is still squared up for us, which means what we're seeing is something accurate in what it should look like. So it actually is an oval. Does anybody know the mathematical word for oval? Okay, that's okay. I didn't think you did. I don't think we talked about it yet. I just was curious. It is an ellipse. Y'all know what elliptical machines are? They're called elliptical machines because that's the shape that your foot makes. Like if your foot was going to draw something when you're on an elliptical machine, it draws an ellipse. So it's an ellipse. So to graph this particular one, we're going to go from, we put a point at -2 and 2 on the x-axis, 3 and -3 on the y-axis, and then you just kind of sketch it in to make it look elliptical. That's an ellipse. So now, when we look down at our conic sections, which one do you think it would be? D. Like now D seems like it shouldn't be B, right? It should be D, because here's what happens. The circle, when you come and the plane slices through parallel, that's the circle that you get right there, okay? When it comes and it's not, it doesn't go through the base, but it comes in at an angle and it's not perpendicular, that's when you get the ellipse. See the ellipse there? Okay. So we know for sure now, and you might have been able to reason through that with the circle, but you know, we're not sure. So this is D, we're going with that, which means up here, the circle has to be B. We can mark out the D. Okay, everybody good with that? So the line, the circle, and the parabola are the ones that you already knew and knew how to graph. This one, you hadn't graphed an ellipse yet, and you haven't graphed this one yet either, so I'm just going to give it to you in the form that you can put in the calculator, and I'm going to have you do that while I hand out the homework. So y equals plus or minus the square root of x squared plus 1. That's what you would get when you solve that for y. So I want you to go ahead and type that in while I hand out the homework, and then we'll graph it and look at what's going on. Okay, so when I graph it, I get this. This is the one that requires the double cone. This is a double cone, and it's sliced through perpendicular to the base, and so it slices through both of them, and you get this right here, okay? Which means when you look over there at A through E, which one is this? This is A, okay? So this thing is called a hyperbola. And to graph this one, I'm going to give you some key points. We're going to put a point here at 1 and one at -1 on the y-axis, and the point at -3 and a little bit more than 3. We're not getting real accurate here because we're not going to talk about all the ins and outs of it, but just kind of get you a decent sketch for now. And it looks, this will look a little bit more pointy, although it shouldn't be that pointy, than the parabola. It's still curved, but again, we're not going to look at, you don't have to remember what it's called necessarily or do a whole lot with it. It's just, I wanted to, again, kind of relate this to you. Oh, there you go. And so this one is A, which means we can change the parabola to C, and then we're done. Have a great day. Please put your calculators up.